In June of 2026, SpaceX achieved a $2 trillion public valuation, immediately followed by a $60 billion acquisition of the AI coding platform Cursor. Most of that value is anchored in the physical reorganization of space access, driven by reusable rockets and a historic launch cadence. But the acquisition presents a paradox. Why does a company built on metallurgy, propulsion, and physics require an enterprise software generation tool? Because the primary constraint for orbital dominance is no longer physical payload capacity. The true bottleneck is the software engineering required for real-time network orchestration. This architecture merges generative AI software engineering directly into orbital hardware infrastructure. Hardware dominance is the baseline. The next $1 trillion in the aerospace sector will be dictated by orbital software intelligence. Managing the Starlink mega constellation involves coordinating tens of thousands of moving nodes, creating a level of operational complexity that is difficult to overstate. Under legacy models, satellites function as dumb pipes, downlinking raw telemetry to Earth-bound data centers for processing. Commands are then manually verified and uplinked back to the satellite, creating a severe latency loop. Human engineers and static logic cannot dynamically route traffic or avoid collisions at orbital velocities. Cursor provides multi-agent AI frameworks designed to automate these complex, real-time code generation tasks. Maintaining network stability at this scale requires an AI orchestrator to manage the sheer volume of data generated by the constellation. The technical integration begins on the ground. xAI provides the raw cognitive models, while Cursor functions as the multi-agent orchestration layer. Inside terrestrial sandboxes, specialized agents generate and test aerospace code against simulated orbital conditions. This multi-agent iteration happens at a pace manual certification processes cannot match, allowing SpaceX to cycle through thousands of tests, while traditional contractors are still in the QA phase. Once the code is automatically validated, lightweight inference models are prepared for orbital deployment. Trusting AI-generated code in aerospace requires rigorous automated oversight to ensure mission-critical systems remain stable. Automating the software engineering lifecycle allows SpaceX to shrink R&D timelines and change the baseline economics of space operations. The hardware remains the primary gating factor. Standard high-compute GPUs fail rapidly when exposed to the harsh vacuum of space. Cosmic radiation induces bit flips that destroy complex machine learning inferences at the silicon level. Deploying Cursor software to orbit requires radiation-hardened AI chips as a physical prerequisite. These specialized architectures are meticulously integrated into Starlink nodes to manage the intense thermal and power constraints of orbit. Cursor agents are embedded directly onto these chips, enabling continuous software updates via laser crosslinks. This bridge transforms passive satellites into active, intelligent computing nodes, setting the stage for decentralized networks. This is the realization of space-based edge computing, where data processing happens directly in orbit rather than on terrestrial servers. AI models optimize constellation routing, predicting demand spikes and managing laser crosslinks to route traffic around congestion zones automatically. Autonomous navigation algorithms allow the mesh to process sensor data and physically dodge space debris without any human oversight. This architecture processes Earth observation telemetry instantly, sending only the relevant synthesized insights back down to the client. The result is a self-healing orbital data center, completely untethered from ground-based computational limits. SpaceX is transitioning its business model from physical asset sales to orbital compute as a service. The industrial sector now faces a reality where software deployment speeds are the primary competitive differentiator for defense contracts. Traditional contractors relying on billable hours for manual flight control updates are challenged by the efficiency of automated AI generation. Terrestrial cloud providers face a new threat as high-margin defense and logistics workloads migrate to sovereign space networks. Traditional telecommunications providers lose global routing premiums to AI-optimized orbital laser networks. By verticalizing launch, hardware, and AI software into a single loop, SpaceX forces the entire industry to either modularize or become obsolete. The market potential for AI-driven space operations is projected to surpass $100 billion by 2035. This creates a secondary market of space applications, generating software-like margins in an industry historically characterized by heavy industrial economics. Integrating Cursor provides the software automation required to translate this orbital infrastructure into a high-margin business segment. Global enterprises and governments must now purchase sovereign orbital compute to remain competitive. The vertical integration of launch, hardware, and AI creates an unassailable monopoly over the solar system's first autonomous computational network.